All right, so these are the notes for Wednesday, March 1st rather. So the first part of this, it says the graphs of f prime and f double prime are shown on the same set of coordinate axes. Which is which? So they want us to figure out which would be the original function, which is the derivative, which is the second derivative. This isn't so bad, and I'm sure most of you can just figure that out because of what we know about the powers of the exponents. What happens to the powers of the exponents as we take the derivative? It decreases by 1, doesn't it? So then we can see that because this is a cubic function, that's going to have to be the original function, f of x. This would be x squared, so this would have to be the first derivative. And then the line is the one that would have to be the second derivative. So it's pretty easy when it's like this. But what we're going to be doing is you're going to be given the graph of the first derivative, and you have to be able to go backwards to the original function. Let's look at some characteristics here. This is my first derivative. Okay? Can you see how from negative infinity until I get right here, these are positive values on that derivative. So what that would mean is that the original function had to be increasing over that interval. These are negative values on my first derivative. So my original function had to be decreasing over those values. These are positive values on my first derivative. So from this x value right here, see how they line up? This had to be increasing. That's the way we have to think of it. So now we have an upside down parabola. This is f prime. So I have to think backwards about what the original would have looked like. I know it would be something like this, but I don't know exactly how it looks until I think a little bit harder about the way that this function is graphed. What I want to see is that from negative infinity until I get to 0, f prime is negative. What that would mean is that the original function would have been decreasing until I get to 0. At 0, at x equals 0, f prime equals 0. So what that would mean is that f would have to be a max or a min, and we'll see which one it is here in just a minute. Because whenever our slope is 0, that means that we have a change from increasing to decreasing or decreasing to increasing. So then if I look at this derivative from 0 to 4, f prime is what, guys? What are these values? Are these values for f prime positive or negative? Positive. So f prime is positive. So what does that mean about f? It would have had to have been increasing or decreasing. If the slope is positive, then the original function was increasing. So look at this. Our function went from decreasing to increasing, decreasing to increasing. So what would we have to have right here at x equals 0? Decrease to increase. Minimum, right? All right, so now let's keep looking. Right here at x equals 4, f prime is 0 again. So that means f would have to have a max or a min. From 4 to infinity, f prime has negative values. So that would mean that the original function had to be decreasing. So if our function went from increasing to decreasing, then what would we have to have right there? What is it, a max or a min? Max. So now let's think about this. We have to have a function that's decreasing, increasing, decreasing. Decreasing, increasing, decreasing. So I know the basic shape, but now I have to get some more things in here. I know that it's decreasing until it gets to 0. So the function had to be decreasing until it gets to 0. I don't know how high or low this is, but I know it has to be decreasing until I get to 0. Then it has to be increasing until I get to 4. And again, I'm not sure how high it goes, but I know it has to be increasing. And then from 4 to infinity, I know the function has to be decreasing. So what I would be looking for is this. I would be looking for a function that goes in the right direction, first of all. It needs to be a cubic function. Then I would look for this. If there's where the slope is 0, those should line up. Here's where the slope is 0. Those should line up too. And they do. That's a lot harder going in that direction, isn't it, than going in the other direction. Now, we also have to graph the second derivative. For the second derivative, I'm going to have to think of either the slope of the first derivative or the concavity of the original. I'll do it based off of the concavity. Look at this, guys. The original function, until I get to 2, the original function is concave up. So I know that f double prime is going to have to be positive from negative infinity to 2. And then from 2 to infinity, I know that the second derivative is going to have to be negative because it's concave down. So I need a function that's always positive over this interval and then always negative over this interval. In other words, the values have to be positive, the values have to be negative. What would that look like, guys? And then at 2, I know it has to be 0. It has to be 0 at 2. So I know I'm going to have this point right here. Would it be A, bless you, B, or C? Yep. It's got to have positive values, then it has to switch to negative values. Very good. So it's going to have to look like that. That's what the second derivative is going to be. So again, that's kind of a tough way to go, but that's the way you have to think about it. All right. Question. Can a function cross its vertical asymptote? What do you guys think? Can it cross? No. Never cross a vertical asymptote. Can a function cross its horizontal asymptote? Yes. This happens all the time. We've had many functions where we have this horizontal asymptote. We might have vertical asymptotes. They look like this sometimes. Crossing the horizontal asymptote. It could also be in this case. I could have a horizontal asymptote here, and I could have an X-intercept, which would cause it to come up and cross and then come back down. So that happens too. If we have an X-intercept, the function's going to cross, and then it's going to come back down. So these are two cases where we cross the horizontal asymptote. Let's go over here to our next set of notes. It says to sketch the graph of the function using the provided table to organize the data. Be sure to use critical numbers, vertical asymptotes, and possible points of inflection in your table. Label, if any, the intercepts, relative extrema, points of inflection, and asymptotes. Also state the domain and range. All right, so let's go ahead and get started. I always like to start with the vertical asymptote. Bill, what's the vertical asymptote? Make sure you write an equation, x equals 2. From here, I can see if I have any x-intercepts. To find x-intercepts, I have to take my original function and set it equal to 0 and solve. First, I should try to factor. Are there numbers that multiply to be 4 and add to be 2? No. So what other method could I use then to solve this? Quadratic formula, right. So I can do negative b plus or minus the square root b squared minus 4 times a times c. Why is it that I could stop right there? Right, I'm not allowed to have a negative under the radical. Right here I have 4 minus 16. As soon as that happens, I know there are no x-intercepts. So whenever that numerator can't equal 0, because to find the x-intercepts, we set the function equal to 0, we have none. Critical numbers come from setting the first derivative equal to 0. That means setting this numerator equal to 0. So we have two critical numbers. Possible points of inflection come from setting the second derivative equal to 0. Can the second derivative ever equal 0? No. So we have no possible points of inflection. Okay, what about other asymptotes? If we have a higher degree on the top, what kind are we going to have? Slant. So we're going to have a slant asymptote. So we have to think, what's the number that would make the denominator 0? It's 2. And then we can use our synthetic division like we did in the warm-ups. Bring this down, multiply, add, multiply, add. This doesn't matter. Right there is our slant asymptote. Just y equals x. So we've got that. What about y-intercepts? Plug in 0 for x. 0, 0, 0. What's it going to be? -2. Now, in our chart, all we use are the vertical asymptotes, the critical numbers, possible points of inflection if we have them, but we don't have any. So we're going to have to go from -infinity to 0, 0, 0 to 2, 2, 2 to 4, 4, and 4 to infinity. When we're checking our test values, we don't need to know this. I'm just going to mark those out. I'm going to put -1 into that first derivative. I want to recognize that in the first derivative, the denominator is always going to be positive, so I don't even really have to deal with it. I'm going to think of the numerator as x times x minus 4. That's all I have to substitute in for. Plugging -1 in there, I'm going to have a negative times a negative. That's a positive. Plugging -1 in over here to my second derivative, -1 minus 2 is negative, cubed is negative. The numerator is always positive, so that's negative. So what this tells me then is that my function is going to have to be increasing and concave down. Remember that 0 is a critical number. I want to find out if it's a max or a min. When I plugged 0 back into the original, I got -2. 1 into my first derivative. Positive times a negative is a negative. 1 into my first derivative, positive over a negative is a negative. It's decreasing and it's concave down. So what does it mean if my function went from increasing to decreasing and that's a critical number? It's a max. Okay, plugging 2 back into the original, that's undefined. And what do we already know about it? Vertical asymptote. Remember, if you see undefined here, here, and here, it has to be a vertical asymptote. Anytime it makes the original undefined, it's a vertical asymptote. 3 into our first derivative. That's a positive times a negative. That's a negative. 3 and over here is a positive. So we're going to be decreasing and concave up. 4 back into the original. 4 squared is 16. 2 times 4 is 8 plus 4. 4 minus 2 is 2. So I have 8 plus 4, that's 12 over 2, and that's 6. And 4 is a critical number. So I want to check it and see what happens. Plugging 5 into our first derivative, that's going to be positive and positive, that's a positive. 5 into our second derivative is also positive. So it's going to be increasing and concave up. What's 4/6 going to be then if we go from decreasing to increasing and it's a critical number? minimum. So now, putting all of this together on our graph, we have our line. Our slant asymptote was y equals x. Looks like that. Y-intercept of 0, slope of 1. We have a vertical asymptote at x equals 2. We have the point 0, negative 2, and we have the point 4, 6. So we know that much. Now we're just going to look at our graph. So from negative infinity to 0, we had to be increasing and concave down. That's going to look like this. These asymptotes are boundaries. From 0 to 2, we had to be decreasing and concave down. That looks like that. From 2 to 4, I had to be decreasing and concave up. Decreasing, concave up. And then from 4 to infinity, I had to be increasing and concave up. And so can you see that? Can you see why this is a maximum? Even though it's way down here, this is still a maximum. Because relative to the points around it, it's a high point. That point right there at 4, 6, that point has to be our minimum. Because even though it's a low point, even though it's not lower than the other one, it's still low compared to the ones around it. Okay? So that's what we're doing now. Some of these might have slant asymptotes on what you're doing today. But guys, remember, if there's no denominator, it's just a continuous function, right? It's just continuous. Only when it has a denominator does it have vertical asymptotes. If I took that away, just look at that for a minute. If I took away that denominator, that's going to change the way it looks completely. See, if I'm on y equals and I just did x squared minus 2x plus 4 and just graph that, that's just a parabola, right? But if I change it to having it so that it's now going to be a rational function, it changes it completely. Now it looks like this, what we just graphed. Okay? So big difference between rational functions and just polynomial functions. All right.